All right, welcome class. This is Mr. Ryan, and since I am not here today, I decided to record my notes for you so that you can still do the assignments. Isn't that nice of me? All right, I'm sure you appreciate that. So, here we go. We are going to learn about electron configuration today. Electron configuration, very simply put, is the address of where every single electron is located within an atom. So, as we recall from last chapter, atoms are made up of electrons, neutrons, and protons. Electrons, neutrons, and protons. And the protons and neutrons are in the center, and the electrons are around the outside in what we call the electron cloud. So, move this out of the way. So the electron cloud contains all the electrons, and if scientists can figure out exactly where all the electrons are located, we suddenly know a lot about the atom. We know a lot of properties about the atom. So that's why electron configuration is important. If we know where each electron is located based on certain patterns, we know if it's a very reactive atom or a very non-reactive atom. We know if it's an explosive atom. We know if it's a noble gas and it doesn't react with anything. We know if it's a metal. We know if it's a non-metal. So by looking at where the electrons are placed, we can tell a lot about an atom. So that's what we're doing today. We're learning where all the electrons are located, and then you'll write out the address for some atoms, which I like to call the electron configuration. All right, so first of all, atoms. They have four types of regions in them, four types of orbitals. These orbitals are labeled the S, P, D, and F regions. S, P, D, and F regions. I'm not sure of the derivation of the letters S, P, D, and F, but that's what scientists use to call the different regions that electrons are located. They're called orbitals, once again. Orbitals. All right, so let's take a look. I drew an orbital down here. And if we look at this orbital, think of the nucleus right here. Think of the nucleus as like a black hole that's trying to suck in all of the electrons to the center. The electrons, though, they move around really fast. Okay, they're moving around fast, and they have lots of energy. So they don't get sucked all the way into the nucleus, but the nucleus is definitely attempting to suck them in. But the electrons, they have so much energy, they're able to buzz around. Now you see, I have this here. This is actually what a p orbital looks like. It has a certain shape to it. And in this p orbital, there's a whole bunch of electrons buzzing around in very seemingly random patterns. And as they buzz around in random patterns, as they move around in random patterns, the nucleus is trying to suck them in. Okay? Notice I drew 1, 2, 3, 4, 5, 6 electrons. That's because in a p orbital, there is only 6 electrons ever. And we'll get into more of the numbers in a second here. Okay? So I like to think of this orbital too as kind of like a fence. And this fence is surrounding the electrons, keeping them in. So we got like a cowboy rounding up these electrons, not allowing them to escape the fence. We also have the black hole that's trying to suck in the electrons towards the center, but they never get there because they move around so fast, they have too much energy, and they don't get caught by the black hole. The actual word for it is the effective nuclear charge, but I like to think of it as a black hole. All right, next slide. Each orbital has a maximum number of electrons that can fit in it. So s orbitals, they can fit in 2 total electrons into an s orbital. So s orbitals, they have a shape of circles. And here's the electrons buzzing around in these circles. You see 3 circles there. Those 3 circles represent different orbitals, and if we were to overlap them on top of each other, that's what it would look like if we were to put them all together, all on top of each other as one big atom. Okay, so once again, s orbitals can fit 2 electrons, and we'll get into these numbers more in a second. You saw a p orbital in my first slide. Remember, p orbitals, they can fit 6 electrons. Now, I have 1 electron here, 2 electrons here, 3, 4, 5, 6. Once again, envision all of these orbitals overlapping each other, and as they overlap each other along with the s orbitals, we start to get some very complex shapes of what an atom actually looks like. All right, once again, p orbitals, 6 electrons. Next, d orbitals. Look at these d orbitals. These d orbitals get very complex. As we can see, we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 9, 10 right here. So 9, 10. And all these would overlap each other to create this very complex fence-like system where these electrons will be located. Once again, d orbitals can fit 10 total electrons. Next slide. F orbitals. F, now look at these complex shapes. You might be starting to wonder, how in the world do scientists know that the orbitals actually look like this? That's a discussion for another day and involves statistics and probability, but it is a pretty complex science to figure out that they have exactly these shapes, and 14 electrons fit into them. We won't be working too much in the f orbitals, so we'll be working mostly in the s, the p, and the d orbitals. Okay, now let's go to your sheet here. So on this sheet, this shows us how we establish the address or the electron configuration of an atom. In other words, where is every single atom within or where is every single electron within an atom located? And the way this thing works is my star is on the path of my traveling finger here. We start with 1s, and we're going to fill that orbital. Then we go 2s. Then we go 2p and 3s. Then we go 3p and 4s. This is the order in which the orbitals get filled. 3d, 4p, 5s, 4d, 5p, 6s, and so forth. Okay? So I just wanted to show you what the electron configuration chart looks like. So when I start to talk about these things like 1s, 2p, 3d, what I'm talking about here. And I'm talking about exactly the space where these electrons are located. Okay, let's skip this. All right, so here we are, and here's what electron configuration notation looks like. So let's translate what exactly this 1s raised to the 1 power. Okay, what does this mean? Okay, I need a little box here so I can illustrate things. So I'm going to draw a box. Okay, that's good. Full screen. All right, so you can see we've got an exponent here. We have this s, and we have this 1 in the beginning. We'll explain exactly what each of those things mean. This happens to be the electron configuration of hydrogen. So this address right here tells us where hydrogen's electrons are located. So what this translates to, translation is, for hydrogen, there is 1 single electron located. Sorry, I just had somebody at the door. I had to send them away. They thought I was crazy because I'm in my room talking to myself. Sorry. All right, anyway. So 1s1, electron configuration of hydrogen. So what this first number 1 means, this 1 right here means in the very first orbital. And what I mean by the first orbital, that means closest to the nucleus. The bigger these numbers are right here, the further away we are from the nucleus. This number right here, this represents the number of electrons in that first s orbital. There is 1 electron. So once again, in that first s orbital, there is 1 electron. And this is for hydrogen. So here's my translation again, right down here. For hydrogen, in the first s orbital, there is 1 electron. All right, so let's do a couple of electron configurations, and I think you'll get it. It seems complex. It seems like, oh my God, what are we doing? But it really is not that big a deal. Okay, so remember, I said in an s orbital, there are 2 electrons. In a p orbital, there exists 6 electrons. In a d orbital, 10, and in an f orbital, 14. So I would advise you to write these things down on the side of your electron configuration sheet. Okay? I don't need these in there for right now. I'll put these in later. Explain why I have those. Those are gone. I'll use this little circle as my marker. There we go. All right, so if we had to write out the electron configuration for magnesium, find magnesium on the periodic table. I'll give you a second. All right, did you find it? Did you find magnesium? It is located, and I just pointed to the periodic table. I'm sure you didn't see that. But anyway, it is located at element number 12. So I'll write the symbol here. So magnesium, it is element number 12. All right, if it's element number 12, how many electrons does it have? 12 is its atomic number, by the way. So if we have magnesium, 12 atomic number. If we have 12 for its atomic number, that means it has exactly 12 electrons. Okay, if it has 12 electrons, we're going to need to map out every single one of those 12 electrons and where do they go. We're going to use this little table up here, the electron configuration table, in order to map out where every single one of those electrons goes. So let's go ahead and do it. All right, I gotta get some stuff out of my way here. So looking at this table here, we're going to start right here. We're going to go 1s, and then we're going to actually write out 1s. How many electrons can fit into an s orbital? Remember this? 2. We can fit a total of 2 electrons in an s orbital, so I'm going to put a 2 right there. See this 2 that I put right there? That 2 represents the 2 electrons that can fit in there. Remember, I am counting up to 12 electrons. So I got to keep on doing this till I account for 12 electrons. 1s2.
The results of full voting for the elections are as follows. For President, Donald Trump, 159 votes, 65%. Hillary Clinton, 61 votes, 25%. Gary Johnson, 14 votes, 6%. For the U.S. House of Representatives, Mike Gallagher, 175 votes, 74%. Tom Nelson, 61
We'll
votes,
resume after the
26%.
announcement.
For U.S. Senate, Ron Johnson, 128 votes, 53%. Russ Feingold, 96 votes, 41%. Freedom predicted correctly. The other following students to the office, please. Brody Bazil, Tanner Brockman, Sam Erickson, Colton Keenan, Parker Rudy, Vince Bougie, Alex Lansford, Jake Schreiber, Joaquin Garcia Petit, Adam Bruckner, Cole Lowney, Reeve Cullen, Colvin Beek, Luke Kingle, Lily Erpeldick to the office, please.
All right, hopefully you fast forwarded through that. We didn't need to hear the election results again. All right, so we got 1s2 so far. That means in the first s orbital, there is 2 electrons. So now let's go back to our thing here. Let's follow this to the next arrow, and we get to 2s. So we're going to write 2s. Once again, how many electrons can fit into an s orbital? We said 2. So we will put a 2 right there. Okay, after 2s, we continue along to the top of the next arrow. We're to 2p. So we will write 2p. How many electrons can fit into a p? 6 electrons. So we will write a 6 right here. So far, let's count up the electrons. We have 2 plus 2, that's 4. Plus 6 more, that's 10. We need to get up to, if you recall, 12 electrons. So let's keep going. After 2p comes 3s. So let's write a 3s. And after 3s, how many electrons? S's can fit 2. So we will put a 2 right here. Let's count it up. We have 2, 4, 6 more, that's 10, and 2 more, that's 12. There is the electron configuration of magnesium. Let's try another one. Okay, let's try copper. Copper. The first thing we need to do is look up how many electrons does copper have, and you should see on the periodic table it has 29 electrons. So let's start from the beginning. Let's see if I can copy and paste that chart over here. Let's see. Copy. Next page. Paste. Oh, that's not what I wanted. Back. Copy. Away. Paste. There it is. All right. So we need to account for 29 electrons. Let's start at the beginning. So I'll use this box now, I guess. It's not letting me select it. There it is. Okay. I'll use this box. And we'll start right here. We start right here at 1s. Okay? So at 1s, then we'll go 2s. Then we'll go 2p, then 3s, then 3p, then 4s, then 3d, then 4p, then 5s. We'll just keep going on until we get to 29 electrons. So we start at 1s, and we're going to write 1s, 2, because in an s, you can fit 2. In a p, you can fit 6, and in a d, you can fit 10, and that's all we're going to get to. So let's keep going. After 1s, then we go to 2s. So we'll put a 2s right there. 2s2. After 2s comes 2p. So we'll write a 2p. 2p. We can fit 6 in it. That's 10 so far. We have a long way to go. Let's keep going. After 2p comes 3s. We'll put a 3s right there. 3s2. After 3s comes 3p. We jump to this arrow. So we're going to do a 3p. That's 6 in that one as well. We keep going. After 3p, oops, what happened to my box? There it is. Come on. What the heck is happening? There we go. All right. Oh, there's my box. It is disappearing. This is not working good. All right, you're just going to have to follow along. So, after a 3p, okay, after the 3p, we get to 4s. So we'll go 4s, 2. After 4s, then we get to 3d. So I'm going to write it right here, 3d. And let's see how many electrons we've used so far. Because remember, we can only go to 29. We have 2. Plus 2 more, that's 4. Plus 6 more, that's 10. Plus 2 more, that's 12. Plus 6 more, that's 18. Plus 2 more, that's 20. We can fit 10 in a D, but we don't need 10. We need 29. I'm going to put a 9 here. And there it is. We are done with this one. We are done with this one, and we're up to 9. And so we have 9 total electrons in the D. And that will be it for our notes here. Now, you're going to have an assignment on doing these notes here. You're going to have a number of electron configurations. Make sure you use your chart right here. This chart, you use your periodic table. Just simply look on the periodic table. It should tell you how many electrons go in it. For instance, copper, 29 electrons. Use the chart. The chart will get you the exact address of that atom. And then our next lesson will be how does this big, long electron configuration show us how reactive or non-reactive an atom is. And we are done.